In this lecture, we will discuss about the complex numbers and phasors. So this lecture will cover the representation of the phasors as the complex quantity. The representation of phasors, basically a complex quantity in rectangular and polar form. And then we will discuss about J operator. So basically, as we discussed in our previous lecture also, that a phasor is basically a complex number which can be represented in polar form. Okay. So we discussed in our previous lecture that the alternating quantities which are represented by sinusoidal wave can be represented with the help of some phasor diagrams or a rotating vector. Means a rotating vector or a line which is a rotating vector which we also call as phasor, when rotates in anti-clockwise direction with velocity omega, it will give you a sinusoidal wave. Now this is a representation, like if you have an AC quantity, it can be represented with the help of a phasor. So this is a representation basically. In this particular lecture, we will see that what is the another method of representing the phasor or the alternating quantities. So there are like a phasor, because it is a complex number. Okay, it represents a quantity which is a complex quantity. In electrical systems, specifically in AC systems, we generally deal with the complex uh, quantities. And one best example of this is, impedance. We have impedance. So impedance is generally represented with the letter Z, which is equal to R plus JX. So we will discuss this in detail in our forthcoming lectures when we will come to the impedance. However, this is just to make you understand that we have the complex quantities, and that is why we are studying this particular topic. Okay, so phasor, which is a complex number, and complex number, it has a real part, it has imaginary part. So there are two ways by which we can represent a complex number. One is the polar representation, and second one is the rectangular representation. So this is basically the rectangular representation. Right. So a rectangular representation is basically the sum of two components of the complex number, one which is the real component, and the second which is the imaginary component. Unlike in the mathematics, which wherein we take any complex quantity as a plus ib, so we do not use iota. It is not used in electricals or electrical systems for under root minus 1. So we do not use iota for under root minus 1 because I is used for the instantaneous value of current. So instead of using iota, we have some other component that we will discuss in our next slide, which we call as J operator. So instead we use J operator, right? So in the rectangular representation, we have Z is equal to R plus J X. For example, this is how we represent, or any quantity which is a complex quantity can be represented as A plus JB. Okay, so where A is the real part, this is the real part, and this is the imaginary part. Okay, so when you have to represent this as a phasor in two dimension, so it can be represented like this. So any physical quantity, for example, x is equal to a plus jb. So this can be represented with the help of phasor. So we have two axes here. So this is the real part, and this is the imaginary. So we have the y-axis basically is the imaginary, and this is the real. right? Similarly, we have positive real and positive imaginary, and then we have negative real and negative imaginary, right? So, for example, if we have a quantity which is equal to x is equal to a plus jb, so this is j basically. So this vertical axis is j, this one y-axis. So it can be represented somewhere like this here. So we'll represent it with the help of phasor. So this phasor has two coordinates. One is this one, this is b basically, and this is your a here. So we'll say that x is, it is a phasor which is a plus jb, right? So this is, this is how it is represented in two-dimensional space, and it is a phasor representation. So like here, if you see in this particular diagram here, so this is represented in complex plane, so where your va is basically a voltage phasor, right? Okay, so this is how we represent. The second type of representation is the polar representation basically. So how this polar representation is done, that we will see. For example, uh, if you have a voltage which is given by V is equal to Vm sine omega t, for example, and you have some current which is It, it is equal to Vm sine omega t minus phi. So here your It is lagging Vt by phi radians or degrees, right? Or you can also say that Vt is leading It by phi. Now, if we have to represent this in, a space, basically two-dimensional space, or in complex plane, how will you represent them these as phasor? So this would be taken as a reference phasor, basically. So we'll take it as a reference, and this is shown as lagging the voltage by some angle phi. So this is how we represent. So these two equations have been represented here like this. However, these two equations can also be represented in polar form. So in polar form, if you represent, so we have uh, like it is the magnitude first of all. So we have the magnitude which is which may be maximum value, let us say, and then we have the angle. So here in this case you can say that angle is 0 because omega t, you can write plus or minus 0 degree. So this angle is shown here. So this angle represents the phase basically. Okay, so this represents the peak value of voltage, and this represents the phase of voltage, or you can say phase, or you can say the angular displacement of the voltage with respect to the reference phasor, right? How? If you have this, like if the voltage phasor is given like this here, okay, V. So let us say this is the voltage value basically, or Vm magnitude peak value, for example. So if you see, it's at this point of time its value is here, right? So its phase is this one. So its angular displacement is 0. All right. Now the other one, which is the current phasor basically. So current is having some phase which is 5 degrees behind the voltage. So it will start from here, this point. So at this is the, what you say, the phase, not the phase basically. This is the magnitude here. So this is the magnitude, and the phase can be taken like if you take 5 degrees behind, so it is 5 degrees behind. So it will start like this. You have a reference phasor sine wave, and it will remain 5 degrees behind. So this would be the phase difference. This is phi, this is phi, this is phi. So means the peak values here. So here we have peak value of current and voltage, right? So this phi will remain constant here, because if it is rotating with the same angular velocity, both of them, so this phi will remain constant here. Okay, so that means your current is lagging the voltage. And uh, if you have to represent this in polar form, how will you represent it in polar form? So the first quantity, because it is the reference phasor, as you see, so the voltage will be represented as Vm angle 0 degree. So this is the representation of this particular phasor in polar form. Now, how will you represent the second one? The current I is equal to Im, the peak value, and then you have minus phi. So minus phi indicates that this particular phasor is lagging to some other phasor, which is taken as reference. Like here in this case, the voltage phasor is taken as a reference. So with respect to voltage, it is lagging by 5 degree. For example, if you have the representation like this, uh, for example, if we represent V is equal to Vm 0 degrees and I is equal to Im plus phi. So what does it mean? It means that your current phasor is leading a voltage phasor by phi. So this will be shown like this here. So we'll show it here. So your voltage phasor, because it is a reference phasor, so it will be shown on the horizontal axis. So this is V, and your current phasor will be shown here. Okay, so current is leading here. So as far as your polar form is concerned, so we can represent the phasor quantities in polar form in this way. So more precisely, if we talk any complex number, if we have a complex number, let us say x is equal to a plus jb. So this is the rectangular form, right? So the magnitude of this is under root a square plus b square, and the angle here is uh, equal to uh, basically it is tan inverse the imaginary part divided by the real part, right? So it is equal to, let us say, phi or theta, whatever. So the polar representation of this one, so it is given by this one, the magnitude and the angle. Okay, so this is how we represent. So this is the polar representation of this particular you know quantity, complex quantity, which is representing some uh, a signal which is bidirectional signal, and its polar representation is here. Okay, so in this slide we have understood that phasor is a complex number. A complex number has two parts, real and imaginary. So there are two basic forms of representing a complex number. One is the polar representation, second is the rectangular representation. This is the rectangular representation, and this is the polar representation here. So in polar representation, we have the magnitude, we have the angle. The magnitude basically represents the length of the phasor, and this angle represents the phase of this particular phasor. So let us understand this with some more example here. Like if you see, there are four phasors shown of some arbitrary alternating quantity. These phasors belong to some arbitrary alternating quantity. So if you see this phasor here, so you can relate this with the quadrants. Basically, you can draw a quadrant here, and you can draw like this is the real axis, this is the imaginary axis, this is negative real axis, and this is negative imaginary axis, right? So now this phasor is in first quadrant here, so it is positive, its length is positive here. Generally the length of the phasor is taken as positive in all the time, means the magnitude will remain positive generally. Okay, it will remain positive, but the quadrant relation which I have discussed, why we are showing it as in the quadrant basically, that is to understand this angle here. Okay, so how did we get this 45 degree? When we have compared the position of this phasor with respect to some reference phasor, so this real axis becomes the reference phasor here. So this angle is 45 degrees here, right? So this is the polar representation. So this 8.49 is basically the length of this particular phasor, or the magnitude of phasor. And this 45 degree is its angular displacement. So this is, I'll just draw it once again. So this is real, this is, you can say, imaginary. So this 45 degree is the angular displacement of this particular phasor in anti-clockwise direction, right? Either you can write it as 45 degree, or you can also write it like this: 8.49 angle and minus what do you say, 315 degrees, because this is lagging this one by 315 degree. This phasor, let us say it is some x phasor. Okay, it is leading this real axis by 45 degree, or you can say it is lagging the real axis by 315 degree. So both are same, right? Both representation are okay, acceptable. Like here in this case, if you see, you take a reference phasor here. So this is lying in the fourth quadrant. So this is the fourth quadrant here, right? So this is the real part and this is the imaginary, minus imaginary here. Now if you see, 8.06 is the magnitude of this phasor here, and 330.26, so this is the angle it is making with this real axis. So this angle is 330.26. However, you can write it in this way also, like it is lagging. So this is the real axis, and we are, no, leading and lagging we discuss by taking the anti-clockwise direction as convention. Okay, so if, okay, now this is 330 degree. However, you can also take it as that this particular phasor is lagging the reference phasor. This is the reference phasor. It is lagging the reference phasor by 29.74 degrees, right? So both representations are same. These are the polar representation, the magnitude and the angle. So why I am saying that this is the magnitude, this is the magnitude of phasor, this is the angular displacement of the phasor. Or you can say phase of the AC quantity to which this phasor belong. Okay, phase of that particular quantity. Okay, so if you draw it, because we know that any phasor rotating with some velocity in anti-clockwise omega will form the sine wave. So let us form the sine wave here. So this is your omega t, and this is your, let us say, xt, which is the quantity, which is this phasor, basically the instantaneous value of this phasor. So it is here, where it is 29.74 degrees lagging the reference phasor. So we'll take 29.74 degree this side. Let us say this is 29.74 degrees. So this quantity will be like this. So it is something like, so it is representing its phase with respect to the reference phasor, reference value. Okay, or you can say it is representing its angular displacement. Like here also, if you see, so we'll have this one. So it is lying in the second quadrant, yes. So this is with the reference phasor, it is making 158.2 degree. So if you draw the sine wave of this one, so it is something like this. Now what you will say, this is leading basically. So this is leading, okay. This is leading, this is lagging, and this is, it may be leading, lagging, whatever. Okay, so leading and lagging are in reference to some, in comparison or in relation to some reference phasor. Okay, so it is leading because, so if your reference phasor is like this, so this particular phasor will start from 158.2 degrees ahead. So it is 0, so it is like here. So it will start from here. Okay, so it is starting 158 degrees, 158.2 degree before the reference phasor, this one, right? So this is how we can understand the phasor and their complex, or what you say, uh, polar form representation or complex representation. Even if you see, if you want to find out its uh, complex value here, so this is because imaginary axis, this is because the real axis. So you can plot a perpendicular from here. So this is, let us say, some x, and this is, let us say, some y, for example. So if it is some quantity a, so a would be equal to x plus jy. Okay, so where the magnitude of A is 8.49 and the angle is 45 degrees. J operator, which is very important. Okay, so as we know that our most of the AC quantities have complex nature. Okay, complex nature. Okay, so generally if you talk about the impedance, which is equal to R plus jx, so instead of using iota, which is equal to under root minus 1, we use j is equal to under root minus 1 because I is used for the current. Okay, so the j operator obeys the same rules, regulations and principle as iota obeys or follows. Okay, because j operator is under root minus 1, and electrical engineering we use j operator instead of, in place of iota. Okay, so j operator commonly used to indicate the anti-clockwise rotation of the vector. So if we see j is basically equal to under root minus 1, right? So if j square we take, it is under root minus 1 square, which is equal to minus 1. J cube is equal to minus j, right? And j4 is equal to plus 1. So this represents the four quadrants basically. So at here, at this point, your j has either 0 power or it is j raised to the power 4, right? At this point it is plus j, which is equal to under root minus 1. At this point it is j square, which is minus 1, and at here it is j cube, which is minus j, and then here it is j raised to the power 4. So this is how we get. So if we say that it is j raised to the power 5, what does it mean? It means that it has one complete rotation and then it is stopping here. One complete rotation, 360 plus 90. So it is 450-degree rotations are there. If it is j raised to the power 6, so it means j4 and then 2 here. So 360 plus 150, which is 540 degrees, right? So it follows the same rules basically as iota follows in mathematics. So it is used in electrical systems in place of your iota, right? So now, how we add the complex number? sorry. So we'll take the, so addition, adding the complex number. Okay, if you have a quantity A which is x1 plus jy1, and if you have another phasor which is x2 plus jy2, so if you want to add these two phasors or complex numbers, so the real part will be added with the real part. Okay, so x1 plus jy1 plus x2 plus jy2. So we will re you know structure this equation as x1 plus x2 plus j y1 plus y2. So the real is added with the real, and imaginary is added with the imaginary part. Okay, so these two are added like this. If you want to subtract these two, a minus b, so again the real is subtracted from real, and imaginary is subtracted from imaginary, right? So it would be a minus b is equal to x1 plus jy1 minus x2 plus jy2. So it would be like this, x1 minus x2, and then we have minus j. So we have y2 minus y1, or we can use plus here, so y1 minus y2. So this is how we can represent the subtraction. So these things, this concept will be used in AC systems. So that is why it becomes important to understand the polar representation. So in this lecture we have understood the uh, uh, representation of phasor in rectangular form, uh, as a complex number, right? We have understood that it can be represented in polar form also. So it is like x plus jy. So this is the rectangular representation. So polar is magnitude of the quantity and the phase angle, right? So if you have again two quantities, v is equal to vm sine omega t and I is equal to im sine omega t minus phi. So its polar representation is vm angle 0 degree, and its polar representation is im angle minus phi degree. So we are taking maximum values to indicate the magnitude here. Okay, so if you want to represent the RMS values in polar form, so it would be like this, because we know that the RMS value of an AC is the Vm by root 2. So we can write Vm is equal to root 2 V RMS, right? So we can put it here. So the polar representation will become under root 2 V and angle 0 degree, and for current it would become under root 2 I angle minus 5 degree. So this is in terms of the RMS value, right? And this is in terms of the peak value. So this was the objective of this particular lecture, so that we can understand how do we represent the phasors in polar and rectangular form. What is J operator? J operator is nothing but it is the replacement of iota in electrical systems, right? So thank you so much.